like and leave a heart.
There we go. Hello, everyone, and good morning. Welcome to the Vidor Locksmith Show. I'm your host, David Gibson, where we are unlocking the secrets to success in the oil and gas industry, one interview at a time, one technical presentation, one interview, and one technical script at a time. I've got plenty of technical scripts to go over with today because I take about a month off, and then all of a sudden I can't do anything right. So it almost seems like there's a bit of a lag. Wow, that seems odd. That's never happened before. Looks like there's a bit of a lag just as far as what I'm seeing on my screen, but that's okay. I don't need to see myself. Just need to be able to talk to you guys. As always, guys, let us know where you're watching from. Love to be able to give everybody a shout out here on the screen as we go through. Like I said, took a little bit of time off, was traveling over the last month, and I was at the SPE IADC SPE conference in Stavanger, Norway, which was absolutely amazing. Then the following week was in Belgium and in Germany, running around working on a robotics documentary. Speaking of which, our guest today is somebody that I met in person while I was there in Germany, Dr. Erik Feldmann. So he will be on the show today to be able to talk about hammer drilling. So we'll bring him up in just a minute as well. Oh, because Tracy's on top of things and I keep forgetting them. We're going to be giving away a drill bit today. So let's go through and say hi to everybody. But don't forget, we will be giving a drill bit away here in just a second. So Paul Moore says good morning. Thank you, sir. Pete Gupta says good morning. Duncan says he's in from H-Town. LinkedIn user says hi all. John DeWart tuning in. Good morning from wet Colorado. Lots of snow runoff. Gail Deering says, good morning. As a former coworker of mine. Thanks for tuning in, Gail. Anoop Sharma says, hi. Thanks for being here. Adele says, hi. I hope. Nice day. Well, thank you, sir. Soren says, hello from Copenhagen. Jeff Chestnut tuning in from Houston. Thank you for being here. LinkedIn user, good morning from Tomball, Texas. Oh, Robert Estes, thanks for being here. Haritz says, good afternoon. And then Adele, industrial maintenance and electromechanical engineer. I am currently looking for a job. Is there anyone who can help me? I think the person that can help you is you. So, posting on here might be a way to be able to get your name out there, a little bit of marketing. But my suggestion would be post on LinkedIn every day for 30 days. Get over your fear of posting and do everything you can to be able to add to your resume. All right. So somebody's also texting me. But it's showtime. All right, guys, I'm going to run a quick little, we do have a sponsor for the show. So I want to be able to say special thanks to Patterson Energy for that. So if you want to win yourself a drill bit, type in hashtag, oh gosh, wait, don't do it yet. I am so out of, now y'all can do it. All right. Now if you want to be able to get one, go ahead and write in hashtag PTEN Patterson Energy to be able to win yourself a drill bit. I am so out of my rhythm today. Sorry, you guys. Please bear with me. But yeah, if you guys want to win a drill bit, we'll be more than happy to be able to send you guys off a drill bit. Hashtag PTEN on the screen right now. All right, let me jump back over here. And play y'all a quick little teaser video.
Our newest alternative power technology is perhaps the most exciting as Patterson-UTI expands the use of lithium-ion battery technology in our rig fleet. EcoCell is an energy management system that uses stored energy to decrease the number of generators needed online and keeps generators running in their most efficient power to emissions ratio range.
There we go. Quick little message about. Oh, sorry, Manoj. I am live streaming right now, boss. Quick little message about the EcoCell there from Patterson. So yeah, if you want to win yourself a drill bit, go ahead and type in hashtag PTEN All right, there we go. Let's see. Did we start getting some in there? All right, LinkedIn user. Yep, that's the way to do it, you guys. All right, keep doing that. Keep going. And here's what I'm going to do. I'm actually going to come back over here, click on this. I am out of my rhythm today. All right, go back over here. There we go. I'm not going to give away the drill bit just yet. We'll let some more people be able to get their stuff in there. But what I do want to do is be able to introduce our guest of the day. Make sure I've got all this stuff set right. There we go. And welcome to the show, Dr. Erik Feldmann. Dr. Erik, thank you so much for being here, sir. I do appreciate it.
You're welcome. Nice to be on your show. And I'm very happy to see you again after your visitation in Germany.
Yeah, and I love the nice little green drill bit you guys have got there.
Yeah, we were very happy to receive one. And we have it here on display in our digital drilling lab. So it was very kind of you to bring it along with you.
Well, tell our audience a little bit about yourself. Obviously, I know where you guys are. I know the lab that you're in. It's a very interesting one. But, give our audience a little bit of background on who you are and where you're at right now.
Yeah, so I work at the Clausthal University of Technology here in Germany. And what I do is I focus mainly on hammer drilling in my research area. But at the same time, I also do teaching some basic level drilling courses for the students here. And here right now we're in the digital drilling lab. So this drilling lab has evolved steadily over the last 7 years that Clausthal University of Technology has participated in the robotics competition, which is organized by DSATS and SPE. And so here our students come in and start working on small-scale drilling rigs and drilling technology in this lab setting. And we try to teach them or enable them along with the competition to get a better understanding of the drilling process, drilling technology, and the interdisciplinary work in particular that is required to achieve drilling a hole.
Well, excellent. Well, for anybody that is watching, if you guys have any questions throughout today's discussion, please be sure to throw them out there. Would love to be able to throw them over to Erik and be able to have him answer them. So I want to be able to jump into your specialty first. It's an area that I know exists, but I know almost nothing about, which is hammer drilling. So can you give us some of what would be the base level information that you would teach either to a new student or somebody even in the industry that doesn't know anything about it?
Yeah, hammer drilling. Well, where to start? Probably it's best to look at the rocks. Yeah. So hammer drilling has some benefits when it's applied in hard formations. So let's put this into perspective. Conventional oil and gas drilling has mainly focused on drilling into sedimentary basins, right? And with hammer drilling, or sedimentary layers are generally a bit softer, let's say. There are some exceptions. There can be very hard sandstones and so forth, and limestones as well. But if we look at rocks of crystalline origin, yeah, then these are usually very tough to build, and their drillability is very, very hard. And this is where the rock destruction process of hammer drilling can or could substantially increase, for example, key performance indicators like the rate of penetration. And so this is something that we try to work on and investigate here, and basically develop downhole tools that apply this rock destruction method of percussion drilling, let's say, or hammer drilling, to improve the drilling process. Yeah. With a particular focus, of course, always back in mind for geothermal applications. Yeah. But it's always very important to remember that here we're in a research area still. So where the application later will be, this is something that the technology will determine itself then at the end of the day. Yeah.
So with that said, is this something that could still be used in, typical drilling that's taking place today, like you said, in a sedimentary basin, or would it be more specifically focused on the harder rock, just the harder rock?
I wouldn't exclude it from drilling in sedimentary basins or in softer rocks, but then you have to look at the bedrock interface a bit closer. And maybe it's very important to take a look on how the drill bit is designed to make it feasible for more formations, right? So with hammer drilling, first of all, we are always looking to generate some sort of an impact downhole. It is then transferred through the insert on the bit into the rock formation. Yeah. And if it's too soft, there might not be, or if the formation itself is too soft, the insert might penetrate, but it might not break away little rock chips, as it's more common with the more brittle rock behavior. Yeah.
So obviously, then with doing hammer drilling, you would have to have a specialized bit just for that application.
Yeah, so generally hammer drilling bits, they don't have cutting elements, right? So they consist of, let's say, inserts that are placed on the tip of it, and they can be either of round shape, conical shape, or ballistic shape. And even the shape of these tips make or have an effect on the rate of penetration for a certain type of rock, of course, and certain type of, let's say, in situ downhole conditions. So it's also a function of, let's say, the downhole pressure in the wellbore itself. Yeah, can have also an effect on the behavior of the rock. So if you have a very high downhole pressure, the behavior of the rock could be more ductile instead of brittle at the end of the day. So in other words, when we drill further down with a true vertical depth, we can then maybe see a different behavior for this for the rock mechanics side. Yeah.
So is there a possibility to still steer a BHA that is set up with percussion drilling or hammer drilling?
I would say it is possible. Now you have to take a close look at the type of steering mechanisms that you're applying. So one thing to remember is when we hammer drill, more or less with a downhole hammer, we have a very large sort of mass in the tool itself that oscillates back and forth. And when the mass travels, let's say, towards the anvil of the drilling bit, yeah, it impacts on the anvil of the drilling bit with a certain velocity. And in this moment, the impact energy is then transferred through the bit into the rock. Yeah, through the bit, through the insert, and then at this interface into the rock. Now, what can partially happen here is that not all of this impact energy is transferred, right? So we have a certain, let's say, energy transfer efficiency, so that part of this energy goes in the rock and part might go back into the drill string itself. Yeah. So what I'm getting to is that you can experience higher vibrations than during regular drilling. And so this is something that you keep in mind and you need to compensate for and design your tool for, to really reduce these vibrations in the drill string and make the hammer drilling possible downhole. Yeah. And then if you have a steering mechanism, obviously this steering mechanism needs to consider this. So if we were to let's say use a rotary steerable system adjacent to this, so this would have to be a finely tuned system with all components to work properly and would need to be tested accordingly. But for easier methods like an adjustable kickoff sub and whatnot, definitely it's possible. Yeah.
So what are the basic components of, I guess, like a hammer drilling drilling mechanism or the tool itself that would go down hole in the BHA?
So there's different mechanisms. So when I talk about hammer drilling, I'm always looking at a hydraulically driven or a mud-driven hammer drill, because we really try to do deep. Yeah? There's a lot of systems already existing that are, for example, pneumatically powered. These pneumatically powered hammers, they're usually used in, let's say, not so deep wells, where they don't run the risk of, I think the translation would be drowning. So where water comes into the well and it sort of drowns out the pneumatic hammer. Yeah. So as we drill deeper wells, we obviously also want to have the benefits that regular drilling fluid provides. And this drilling fluid, with all its benefit, is also supposed to hydraulically power this hammer. Now, there's several mechanisms. There's indirect driven hammers, there are direct driven hammers, and double acting hammers. And essentially, at the very start of hammer development for hydraulic or mud driven hammers, they basically were spring powered hammers that were reset by the hydraulic force, force of springs in the tool. And now we're moving away from this. We're trying to eliminate all springs. And we're using something, at least in many designs, something that's referred to as the water hammer effect. Yeah? So the hydraulic fluid that's pumped, or the drilling fluid that's pumped through the BHA, is more or less interrupted by a valve, which accelerates a piston mass, which is used then, as I mentioned earlier, to transfer this impact energy from onto the anvil of the drill bit and into the rock. And so these are the systems that we are working on, because this would enable us to drill really, really deep. Yeah? And cuttings, transport, and so on would be still feasible. It's much more difficult to transport the cuttings up the hole if it's just pneumatically powered.
So what are some of the big challenges left to overcome to be able to make hammer drilling a reality?
Well, deep hammer drilling, it needs to basically be a mud-driven fluid. So there's different concepts out there. Some concepts use, for example, two types of fluids: a working fluid, which basically powers the hammering mechanism, and the drilling mud fluid, which would then be responsible for the cuttings, transport, and whatnot. So this is very difficult to set up, because either you're running some kind of a pipe that has two flow channels, and this would have to be eliminated. So the system has to be reduced to be really integratable or integrable into the existing drill string as we know it today, right? And this is a challenge, because drilling fluid obviously has very abrasive components in it. So whenever we have tight flow channels, or let's say curved channels in the design, they are often subject to abrasion or erosion due to the drilling fluid that's pumped through to it at a high rate. So this is really still where the development is still needed to improve this, and basically prove that the existing technology, or the technology, is able to have a certain lifetime that's usable for drilling the well. Yeah. So the tripping times, not the tripping time, but the time between trips is longer and more distance is drilled.
So it's the mud's fault.
It's not the mud's fault, because the mud is the beauty and at the same time, and the challenge at the same time. But at the end of the day, actually the drilling mud also has a big benefit, because it transmits the power, right? The hydraulic power downhole. And we're basically just taking a little bit of this hydraulic power to power a very wonderful rock destruction mechanism.
Well, we've got a question that's coming here, so I'll pause on mine real quick. And so Kaylin says, what happens as you drill very deep and the hot rock become more ductile?
Yeah, this is a very interesting question. I mean, at what time or at what temperature is a rock becoming really ductile? This is something that you'd have to look at the different curves. And is it feasible to drill there? So, for example, if we're drilling for geothermal energy, let's say what temperature are we trying to reach? Yeah. So just as an assumption, if we wanted to produce electricity, we'd have to go into a temperature range, let's say, somewhat greater than 120 degrees, right? If we have a single, not a binary cycle, but a single cycle. So this would be assuming a temperature gradient of 3 degrees per 100 meters. So we're looking at somewhere around 4 kilometers depth, you know, to vertical depth, unless there is a temperature anomaly. So if you're trying to go much deeper where the rock is much more ductile, then you would have the possibility maybe to, again, take a look at the bit-rock interface and make some changes to the bit design. Yeah, where we maybe have some, let's say, overlaying techniques between the shearing action and the action or the tensile action of rock destruction, yeah, or failure mode of rocks. And so more or less like a hybrid bit design, maybe something like this, that we've already seen maybe with, let's say, roller cone bits integrated into regular drilling bits. Yeah, so it would be possible to do something like this for hammer drilling as well. Yeah.
Do you see that hammer drilling could be the key component to unlocking more geothermal drilling applications or energy sources?
Well, from this perspective, I would try to look at something different. Let's say if we're looking geologically right now, when we're talking about geothermal energy or deep geothermal energy, we're mostly focusing on, let's say, drilling into hot water aquifers or fault zones, right? But if we look at the spread of these type of geothermal, let's say, targets in the subsurface, they're not everywhere, right? So if we're looking at doing widespread geothermal energy, we'd have to consider different targets. And this is, of course, the crystalline basement, yeah, in a way, because heat is there. We know it's there, and there's just an abundance of it. And if we want to establish drilling technology that can reach in these areas, then I think hammer drilling would be one solution in a whole, let's say, one solution to a problem in this whole challenge, yeah, as a whole. So because obviously geothermal energy to produce it is much more difficult from an economical standpoint of view. So really need to focus on reducing drilling time to reduce drilling costs, yeah, for this. And yeah, does it answer that for you?
Oh yeah, I just want to let everybody know, if anybody else has got any questions, be sure to feel free and throw them out there. How did you specifically get into the hammer drilling, I guess, area of expertise?
How did I? Well, this is a longer story. As a student, we participated in the robotics competition many years ago. This was the first year where we participated from Clausthal University of Technology, and we actually built a really small-scale hydraulically driven hammering device. So this was so small that it didn't generate, let's say, a lot of impact energy, yeah, but it seemed to help the whole drilling process. And this was very interesting. And then here at the Institute, we actually then sort of discovered that there was, let's say, a fairly big history in hammer drilling research that had been conducted previously with the drilling of the continental well of the Federal Republic of Germany, which was a well which was drilled very vertical, and it was supposed to reach as deep down as possible, scientific well. And they finished at 9,101 meters vertical depth. And I think they finished sometime in the mid-90s. And for this purpose, they had also looked at different technologies to drill basically into the crystalline basement, right? Which was expected there. And from the reports that I've seen, I mean, they reached maybe back in the day with roller cone bits somewhere around 1 meter per hour, right? So now you can imagine that this takes a long time to drill, first of all, in a 24-hour shift, maybe 24 meters, something like this, probably a little bit less. And tripping time is just immense, yeah? So this is where the Institute had quite a bit of background in looking at different concepts for hammer drilling. And so we started again to pick up this topic in 2017. And I became a researcher on this topic in particular, and building actually a downhole hammer that we're currently testing. Yeah.
Oh, y'all are currently testing. Excellent. All right, so we've got a couple of questions that have come in. So not to, so this one's from the famous LinkedIn user. Is there a significant difference between hammer drilled cuttings and, for example, PCB drilled cuttings? Is there a difference? If there is a difference, does the mud need to be adjusted? Are there annulus differences, etc.?
Yeah, so there is a difference, right? So I would more refer to as, first of all, as chips, rock chips in a way, because the way the process works, let's just imagine a single insert, and in this case, for simplicity, it could be a conical shape, yeah. So this is just placed onto the bottom of the well, onto the rock, right? And so now we're impacting on this here, and so as the insert penetrates into the rock itself, it sort of crushes everything that's in the area, and there's like a small wedge that's being formed underneath the insert itself, yeah. And this wedge is basically condensed rock material, very condensed rock material. And this condensed rock material, as the tooth or the insert pushes on it, exerts a stress on the surrounding, let's say, rock formation. Yeah. And when this stress, let's say, exceeds the strength of the rock or the tensile strength of the rock, there's fractures that are formed out, and basically there's little rock chips, and they can be already quite large, if I say little, that are formed and sort of, yeah, that are formed and pushed away by the drilling fluid. Yeah. So when we did tests, for example, in granite, we had rock chips that were exceeding 16 millimeters in diameter. Yeah. Just as an example. And at the same time, you also obviously receive smaller, finer rock chips. So if you did let's say a grain analysis curve, you'd have quite a variety. Yeah, but it's different from rock to rock, and also from, let's say, surrounding pressure.
Is there a lot of difficulty in, I know with drilling with PDC bits, going from one formation to the next, right? Going from a hard formation to a softer formation, or soft to hard. that transition zone can be, having to control your drilling parameters can be very important. Is that something as well in hammer drilling, to where you have to kind of like focus in on your drilling parameters, or is it so long as, it's a hard rock, we can just keep blasting through, we don't have to change much?
Well, I guess there's different ways to consider it. Let's just start maybe from one example. So imagine we have a soft layer and then a hard layer, yeah, and it has sort of it's at an angle, like an incline, yeah. Generally, when we drill with a conventional drilling, we have quite a bit of weight on bit, right? So it could actually happen that the bit or the BHA is deflected and sort of follows this incline of the hard rock formation, right? So I think every directional driller knows exactly a lot better than me how this works. But what we can see here in hammer drilling is we generally wouldn't need as much weight on bit because for the shearing action, like on your example here with the cutters, these cutters have a certain depth of cut, so they need to sort of be pushed into the rock to shear away the material. So you need a lot of weight on bit. With the hammer drilling, you need, let's say, good contact between the insert, right? The insert and the formation. You need a good contact, but you don't need too much weight on bit, right? The contact just needs to be there, that the energy or the energy transfer efficiency is very high. So let's say we weren't touching the rock properly, right? It just does something like this. So the energy is not properly transferred into the rock. The benefit here is that you need less weight on bit, and so you wouldn't deflect. This is one or you would run less chance of being deflected. Yeah. So this is one benefit. And of course, in terms, if you're drilling into, let's say, an overpressured formation, it's the same as regular drilling. Yeah. There's nothing that hammer drilling will experience difference, at least from my point of view. Yeah.
There we go. All right, got a question here from Soren. What is the range of hits per minute when hammer drilling?
Yeah, so that's a very interesting question. So there's different designs out there, but generally what we've worked with and is something around, let's say, 15 to 25 hertz. Yeah. So this is 15 to 25 impacts. With our design, we could actually change this quite substantially. But at this range, we have sort of had the experience, or I've made the experience that we were able to set up the drilling process in a way that the rate of penetration was quite well. And we didn't have too many, let's say, effects that were opposing to the drilling process. So as an example, if you have to think of the hammer downhole as sort of like an agitating source, right? Actually, so you could actually develop harmonics and everything in the drill string. Yeah.
So is there any adverse effects that the hammer might create as far as, like, MWD electronics or anything?
No, I wouldn't rule it out per se. What I can share is that we have done tests with MWD technology, and it was successful. So it was we were able to still measure and send information per mud pulse telemetry up the drill string. Now you need to tune your software a little bit at the surface because the hammering mechanism for a fluid-driven hammer has, let's say, a certain signature in the fluid itself, a pressure signature in the fluid itself. So you need to kind of filter this out to read your pulses, right?
Easily done. All right, so we got another question that's come in here from John. Mr. John Jall, is there a hybrid version possible hammer when you hit hard stringers? So something maybe, I'm guessing maybe something that could be activated in a ball drop or something maybe?
It could be possible, I suppose. However, this has not so much been my focus yet on the research side. So I have to be maybe careful in if I can answer this properly for you. Yeah.
Well, John, let us know if you have any follow-ups to that one. Where would the hammer drilling tool actually go in the BHA? How would a typical BHA be set up with this?
So typically, you would set it very close to the drill bit. Yeah, and this is goes back to the idea of basically impacting directly onto the anvil of the drill bit. Yeah. So in essence, when our accelerated mass impacts onto the anvil, right? So let's say, just take this as an example. This is not a hammer drilling bit, though, right? The mass would somewhere impact here, and our inserts on the bottom of this, right? So there's sort of like a shock wave that's traveling through the drill bit into the insert, and so this is where this is why it needs to be fairly close. Yeah, I know any kind of technology always wants to be really close to the drill bit. So I suppose this is where it's really interesting to make a design that a feasible design where you can integrate basically all kinds of different technologies, including kind of sensoring technologies and steering technologies that are close to the drill bit, right? So you're competing for real estate at the end of the day. Yeah,
it's very expensive real estate right there. How long, or does this mechanism also like spin the bit, or do you need a motor that's up above that spins, or is that even, or is there any RPMs at the bit at this point other than, I mean, I guess, do you even need to spin the drill pipe?
So I've seen designs where the let's say the designer on there also tries to rotate or actually transposition the drill bit. Yeah. But this is very difficult to, let's say, realize reliably yet. Maybe in the future we'll have some technology that can do this well. And however, the idea by transpositioning, let's say, the drill bit comes from the idea that when you have an insert, yeah, and it forms this crater of rock chips, basically, that were blown away, it forms like a crater, then the idea is that this crater has a certain size, right? And so the idea was that you want to basically transposition the insert to the optimum place next to this crater, right? And so there was some ideas that were going back and forth on how to do this together with the drill bit design. And this way, the idea is that you always impact onto a new, let's say, not a new area on the bottom hole. However, for us, it's been it's not really improved the rate of penetration yet. So we have made better results with actually turning very slowly. yeah, rotating very slowly, and sort of letting the hammer find the areas on the bottom hole that need work done on it. Yeah.
That sounds like a pretty interesting study. So then there's not really a need to rotate the drill pipe other than maybe to, I guess, break friction to get weight down hole. But then again, you guys don't need as much weight down hole. Is that correct?
So you would still need to rotate because the insert always needs to be placed in a new area, right? So just that it might not be, or you might not need very high rotation. I mean, this is also a function again of the question earlier, your impact frequency, right? So if I have a higher impact frequency, then I could probably rotate a bit faster. Yeah, but it's we are yet to see whether or not a really high impact frequency then really improves the combined with a let's say higher RPM, improves the rate of penetration. So this is maybe something that still would have to where we'd have to have a lot more experience yet in this field. Yeah. Maybe there's drillers out there that have a lot of experience on pneumatic hammers and they have it tuned down already to a T. This might be possible. But for the, let's say, mud-driven versions, this is at least my experience that I can share.
So then another question for me then would be, would it be possible then to be able to use this application in extended reach drilling scenarios where you don't need to transfer as much weight to the bit to be able to efficiently continue drilling?
I think so, yes. I think it's possible. Absolutely. You just have to basically remember that you still have to steer the processor. Yeah. So this is something where basically you have to, or you would have to work together with designers of BHAs to see what would be an appropriate setup, right? In my opinion. So, and once obviously extended reach wells and the design of the BHA is already a very complicated issue in itself, even for conventional drilling. So now we're just introducing basically the new or the different type of technology in it. But I would be confident to say that this could have advantages. Yeah.
So, all right. So we've got a couple of questions coming in here. LinkedIn user asks, how long is the hammer drill assembly? For example, how far above the bottom must an MWD be located?
How long is a hammer drilling assembly? Well, let's say the hammer tool itself has maybe a length of 1 meters and 80 centimeters. So let's say 6 foot, yeah, 6 to 7 foot, somewhere around there. Depending on the diameter, the tool could be laid out in a way that it's even much shorter, right? So clearly, this goes back to the piston mass that we need in the hammer itself. The greater the diameter, the more mass we can have in it, the more impact energy we can basically generate. So it's still we're still able to reduce it in length. And then after that, we have worked at least with a shock absorber tool to basically try to remove any kind of vibrations that would go into the drill string. You can already have your first stabilizer on the hammer housing itself, stabilizer ribs. So this is possible. And right after that, you can already start locating MWD tool, more or less, yeah.
Wow, that's pretty close.
It's close, yeah. but I don't know what the preferences are. I always find when I talk to different industry professionals, every company and every person has sort of their particular setup, beliefs and ideas and experiences. So I would discuss it always individually, maybe.
Everybody's got an opinion in this industry. Quick question: as far as I guess dull grading on a bit, would it doesn't sound like you would like the bit would gauge, or I mean, could the bit even really dull in this instance? Like it seems like you would just be taking the bit out of as far as a wear component out of the possible failure points.
So I think there's still obviously some wear on the inserts. As they're the contact point with the formation itself. So in my opinion, if you have, for example, aggressive inserts like that have a ballistic shape, they could wear down a bit faster, which could maybe slow down the hammer drilling process in itself over time. But it would have to we would have to see which type of materials are out there to use, what is maybe a better material to use than what's currently more or less being used. So for more very hard formations, you often already see on the drill bits, let's say, rounder inserts and not so aggressive inserts. So they tend to last a bit longer, obviously, right? In terms of gauge protection, if you're not, let's say, if you're not rotating so fast and you can keep your rotation fairly steady, you might have a benefit there. But like anything in the oil field, then it probably comes back down to the user and how they set up the drilling process, right?
Yeah, can't take that part out. Somebody's bound to break it.
I've always heard this wonderful saying that if you give your tool, your precious design to the oil field, then they will find a way to break it, and then you're back at the drawing board and starting over again, right?
Sounds very true. All right, so I ask, like on the PDC bit on your desk that you have side cutters, do you have something similar on hammer bits? And do you also have something like an under reamer?
So for our trials, and just remember, Soren, thanks for the question, by the way. For our trials here at the university, we did not do the bit design for the hammer. So we basically focused a lot on the mechanism, the strike mechanism for the hammer. And we used common bits, hammer bits, that were already developed for pneumatic drilling. So these bits did not use any kind of side cutters and whatnot, or PDC cutters on it. But from the trials we did, I'm absolutely convinced that the bits need to be adapted to drilling with drilling mud for two reasons. One is basically to improve the clearing of the rock chips, or the I guess cuttings when you look at this bit. Because with these pneumatically powered bits, this was not very efficient, was our observation. Because we found out that we had some over-drilled cuttings. So the cleaning or the flushing away of the cuttings could drastically be improved. And with this in mind, when you're doing this, you could also improve maybe the drill bit itself for let's say gauge protection and whatnot. And I think there was a question about reaming, maybe.
Yeah, and it says there at the end, and where do you go? And do you also have something like an under reamer?
Not yet. Yeah, not yet, but it could be developed. Yeah.
There we go. All right. Next question up here from LinkedIn user: are conventional shock subs enough to offset the vibration from hammer and hard rock to maintain reliable telemetry?
I think conventional shock subs are very good in what they do. However, I think if you're looking at hammer drilling as a technology, there's definitely ways to improve these shock sub, because it's a different technology in a sense that we have somewhere between these 18 to 25 hertz of excitation in the hole. There is, from a research and development perspective, there's obviously always room for improvement, but at least I could say the experience that we have made with conventional tools was already very good. So we were measuring, for example, accelerations in excess of 100 G, and with commercial shock subs, it was reduced substantially to under 20.
Wow. We did get another question here from Eric, which asked, is any difference in cuttings, shapes, and sizes, which we did already cover, Eric. So I don't know how far back in the conversation that was, but I don't want to have to cover it all again. Eric, so audience has asked a bunch of questions. I've asked a bunch of questions. What question are we not asking of and it's something that we should know about hammer drilling?
What questions are we not asking? That is a good question. Yeah.
It encompasses all the
my question is, where do I find more wells to test, right? This is something that I'm always concerned with. I'm always looking for possibilities to test the tool, to learn more about it. And I think if you want to improve the technology, you really need to go in the hole to make it acceptable within the industry to use, right? This is my biggest question. This is one of my everyday questions, obviously. Yeah, I mean, maybe a user here has another question that hasn't come up yet.
John Dahl does ask, how close does it follow cable tool drilling cutting process?
Cable tool drilling. So you mean like something that's being dropped in the wellbore?
I believe so.
Yeah. I think like sort of like ramming something, I assume. Yeah.
I believe that's the idea of it. Is just, I mean, I don't know. John might need to tell us, but yeah, I think it's just the act of dropping a really heavy something or other down there at the bottom of the wellbore.
Okay. Yeah. So the main difference is obviously impact frequency, and possibly in this case, we from what I've seen, where very heavy objects are dropped in the well, they would be probably working with much higher, let's say, impact energies, because the impact energy is obviously the mass times the velocity, 1.5 times the mass times the velocity squared. So these are the parameters that we're looking at, right? I think this is the main difference. Yeah. I hope this sort of helps.
I said yes, the action of how rock gets cut. So yeah, I think that's what he was asking about. LinkedIn user here says, what sort of typical differences are there on weight on bit?
Mm, well, let's say generally speaking, if you push an insert with, let's say, already 100 kg onto the rock, you have a very good connection between the insert and the rock. So if you have several inserts, like 20 or so, then if you have 2 tons onto onto the drill bit, and the inserts are all very evenly onto the rock, you have very good connection, and you don't need more. Yeah. So generally, if you have 500 kg, between 500 and 1 ton, I would say you already have very good energy transfer efficiency, and this is what we're looking for in hammer.
Okay. John DeWart says, recent drilling in the Utah Forge project demonstrated that PDC bits could drill granite at 100 feet per hour versus offsets at 15 feet per hour. If PDC bits can be adopted for aggressive hard rock drilling, where do you see the application of hammer bits?
Okay, so this is roughly 30 meters per hour, roughly, I guess, versus 15 feet per hour if PDC can be adopted for aggressive hard rock drilling. Well, this is definitely very good results if you achieve 100 feet per hour. One thing to take a look at, though, is that the drillability of rock is not always the same. So it's subject to several influences. So, for example, if you have already some pre-fracturing and whatnot, it could be very fast. So, in my opinion, I would be interested to see if you can recreate this also in other formations, these 100 feet per hour. And if that's the case, it's obviously really good. And then it remains to be seen if you could achieve maybe even a hybrid effect where hammer drilling is combined with maybe something like this, and even increase rate of penetration. So if you're eliminating a different, let's say, rock destruction mechanism from this equation, then you're just leaving it out and you're not looking at possible benefits. But the value of 30 feet per hour is very good. 30 meters per hour is very impressive. Pardon me.
Yeah. Well, Eric, thank you so much for answering all the questions. Anything else that you want to be able to tell the audience about hammer drilling?
No, I'm just very happy that everyone tuned in. Thank you so much for your interest. If you have more questions, you are very welcome to contact me or the Institute, and we can discuss this in further detail. And I believe that it's still a very good technology to follow and to continue. And if we want to exploit more geothermal energy in particular, it's probably very, very interesting to continue doing research and raising the technical readiness levels of this technology.
Well, Eric, thank you so much for being on the show today. But before I let you go, we've got to do something. So if anybody wants, hashtag PTEN, can't really see it that well because the white backdrop there, but you guys know what we're doing here. So if you haven't already, be sure to put that into the comment section now. See if anybody's going to put that in there. Oh, real quick. My mom, Rebecca, you met her. She says, hello, Eric and the team. So yes, big shout out to Harry, Wolfgang, and the rest of the Drillbotics team. Hopefully all of them are watching and liking the show. So let's add this one back up there. Let's see if we got anybody else that put it in their comment. Uh-oh, lost my mouse. There it is. All right, let's see here. Let's give away a drill bit. Ready? 5, 4, 3, 2, 1. That's it. All right, everybody's gotten their thing in there. So, well, once again, Eric, thank you so much for being here. Thank you guys so much for y'all's hospitality while I was in Germany. Absolutely loved it. Paul Moore is the winner for today. Paul, thank you so much for watching the show. Do appreciate it. I've got your contact information, sir. I'll get you one of these drill bits over your way here pretty soon. Special thanks to everybody watching. Special thanks to our sponsor, Patterson. And get this back off the screen. There we go. If y'all want to be able to find out any more about hammer drilling and stuff, be sure to reach out to Eric and the University of Clausthal. Absolutely amazing place. Absolutely beautiful people. And you guys are doing some phenomenal research. And most importantly, best of luck to you and the team in competing in robotics this year. Any predictions?
Thank you so much. Yeah, we're really looking forward to this.
What? Give me some quick updates. What has the team done with the rig since we left?
So I can tell you, last night we worked on machining the steering mechanism till I think 2 a.m. in the morning. So we're really getting close to assemble this, and yeah. A big shout out to Dominic there, and to Kanan that just are doing a very awesome job right now in getting ready for the competition, and we are really looking forward to meeting like-minded students from the University of Mons.
Yeah, great shout outs to the University of Mons there. They were great, amazing students. So I hear you guys said you were machining it. I think Harry said right before I left that y'all were thinking about maybe 3D printing the steering mechanism, possibly.
Yes, as a model, I think it was mentioned. So I'm not sure if. So we basically machined this out of messing. Yeah. Sorry, lost on the translation. Metal. Yeah.
No worries.
Aluminum and like a bronze, I think it's. We want it to be reliably working downhole, right?
Well, I'm really excited to see the final product. Wish you guys nothing but the best of luck, and hopefully I can make it back out there to be able to come see you guys when y'all all get together to be able to compete. So, Eric, thank you so much for being on the show. For everybody out there watching, do appreciate it. Tune back in next Friday. We've got another special guest coming up. Don't have it 100% solidified, but I do believe he just sent me a message on LinkedIn and says he'll be here. So really excited about that one. Man, out of practice on this one. Need to get back into show shape here. That's it for me. As always, know your industry.
Thanks.